I'm going to start by walking you through some of the history of where this came from, this software, and then we'll go through our first basic example of how it works. As we go through this, keep in mind that this software, it is public now, and you can use it. It's intended to be used on, we're designing it for JWST datasets, but it comes from software that's been used for ground-based data, and some of the examples we use are going to be from ground-based data, data from other space telescopes. So it's, in principle, a general-purpose software, and we encourage you, before you have your JWST data, to use it on other data sets to see how it works. With the caveat that this is an active development, and this is definitely a pre-release version of the software. So there will be changes coming and things that we're working on, and Dominica will point out at the end a place where you can submit issues if you find any. Okay, in the Slack channel, I've posted the GitHub page for the software, and in a minute I'll point you to the very early preliminary documentation that we have too. But those are the websites there, so that you can see them. Of course, the problem that we have to solve is to fit not just a single galaxy spectrum, but every spaxel of a data cube. This is not a new problem. This is the need to do this in galaxy spectra has been around for some time, and there have been various approaches. Of course, we want to fit emission lines, perhaps with multiple velocity components, fit some stellar continuum, an Aegean continuum. What's new with JWST is that in a data cube, not just in a single spectrum, we'll fit dust continuum, including PAH features and absorption. And we may even fit interstellar absorption lines. There have been other approaches, other software that has been used to deal with this, but again, we're applying this, really focusing on the JWST specific needs, and that's where we're headed. A little history. So this software is based on an IDL software that I started working on when I was a postdoc at the University of Hawaii, and we gave it a name there, I think because a referee said, oh, you should call this something, so we called it UHSpecFit, the software that we use. That actually branched in a couple directions. One branch stayed at Hawaii and then went off to Australian National University and became the base for Lazy IFU, which is a software package that's publicly available and has been used to fit data from the SAMI Galaxy Survey. It's a multiple galaxy integral field survey conducted with the Siding Springs Observatory in Australia. The Rhodes branch came with me, and we named it IFSFIT, and it's evolved and developed and been used for a number of different papers, not just these here, but some other ones, and various spectrographs. And there is a website for this. IFSFIT is there and usable, but it is written in IDL. And in 2017, we added a specific capability to IFSFIT, focusing on the removal of a bright quasar point source from the data cube to separate the quasar and the host galaxy. And the figure you see on the right here outlines this iterative procedure that we went through in 2017. So this became the basis for what we decided to develop into Q3dfit. So this, when we started working on Q3dfit, it was early in the pandemic, and I was at home, so I made a software. I'm not a software developer by training, so I used an old-fashioned way of my old-fashioned wall and sticky notes to make a block chart for IFSFIT so that we could turn that into Q3dfit. So that's what you see here, and this is on my office at home with strings and other things. The two main routines in Q3dfit that do all the work are Q3df, which calls some other things, and Q3da, and those are the IFSFIT versions of those are highlighted on this chart, and you can see they depend on a bunch of other things. In particular, the main fitting under the hood is LMFIT in Python, and so this is a fitter you may know. We're presently using the nonlinear least squares fitting version of that, but LMFIT can call other fitters from SciPy Optimize, for instance, MC, and we've done a little testing with MC. The stellar fitting is done with PPXF, and then the other continuum fitting is done with some routines that we write. Presently, Q3dfit focuses, as IFSFIT did, on removing the point spread function only in a spectral way. So that was what was unique about IFSFIT compared to other methods that have been used in the past to remove quasar point source light from a data cube. And however, we're working hard on the spatial PSF removal because we're learning that with JWST that's critical because of, and I'll talk about that in a minute, and then some of my other colleagues will discuss that as well. So in 2020, we ported IFSFIT to Python into Q3dfit. In 2021, we worked on incorporating mid-infrared continuum and feature fitting, and so that's obviously critical for MIRI observations with JWST. And the software package that we use for this is called QuestFit, and so QuestFit is a package that was developed for Spitzer fitting back in the 2000s, and this software just simply uses MPFit and single pod templates and some simple black bodies to fit various mid-infrared spectra of galaxies, including both galaxies and quasars. And it's also the basis for the IDEOS IRS database for the heavily obscured sources in that database, which has just recently been made public. So QuestFit, we incorporated that into Python in 2021, and then presently we're focused on working on the spatial PSF decomposition as well as a number of other. That's our main science problem we're trying to address. And so, of course, I'm sure, are aware that JWST in the MIRI band in particular, but also in NIRSpec, there's a strongly wavelength-dependent point spread function. And this presents problems, potential problems when we're doing just a simple spectral decomposition. And there are some other issues too that Andre Vayner will talk about. And Caroline Bertemez, when she discusses the mid-infrared fitting, we'll talk a little bit more about QuestFit. Of course, the PSF has strong spatial variations as well. And that's another issue. This is just an example of simulated PSF removal using in JWST imaging. Of course, in 3D spectroscopy, we have different challenges. The PSF, it's undersampled at most wavelengths, and so this creates some sort of strongly spaxel-dependent ripples in the spectrum.